This video is going to show you how to do, this is 10.47, so chapter 10, problem 47 in Siegel. So consider the weights of two samples of candy bars, both before an intervention, given in the dataset candybar.sav. This was actually a problem from chapter 5. So in Siegel, he refers you back to a certain table in the early part of chapter 5. So you can get the data set from Baboogle. Just go over and click on Candy Bar. And if you do that, you'll see it looks like this. So let's go back to the course packet. Part A says, is this a paired or unpaired situation and why? This problem is maybe a little bit tricky in that you see the before and after, and usually when students see before or after, they think it must be a paired test. But remember, the defining characteristic for a paired test is that you have two measurements on each sampling unit. Now in this case, you've got a candy bar, and the candy bar is going to be your sampling unit. And it's not like you're taking two measurements on that candy bar. So you're measuring the weight. It's not like you weigh a candy bar before you intervene, then you intervene somehow and weigh the candy bar afterwards. Instead, what I think is happening here is that you've got a machine that makes candy bars, and you make a bunch of candy bars from which you sample 20. Then you do something to the machine, and then you make some more candy bars, which would be these after candy bars down here, and you weigh them. So what you've got are really two independent samples of candy bars. It's just that one was produced before some intervention, and the other group was produced after some intervention. So remember the rule in SPSS, one row per sampling unit, one column per measurement. And so that if we have 40 candy bars, we have 40 rows. We have an indicator whether it was before or after the intervention, as well as the weight. All right, so this is definitely an unpaired situation, or otherwise known as an independent sample t-test situation. Now the next thing that we should do is state the parameters in the null and alternative before we go look at our data further. So I'm just going to do this in Word. So let's say that mu sub b is the true mean weight of a candy bar before the intervention. And then we're going to say let mu b, or mu a, be the true mean weight after the intervention. Now the null hypothesis is going to be that mu sub b is the same as mu sub a, which is the same thing. So mu sub b minus mu sub a equal to 0. And then the alternative will be, you can call it h1 or ha, mu sub b not equal, I'll use greater than less than, mu sub a, which is the same as mu sub b minus mu sub a is not equal to 0. Now let's just go read what we have to do. We have to find the mean and the standard deviation, find the 95% confidence interval, and then come to a decision whether the intervention produced a significant change in weight. And then we're also supposed to discuss the variances. So if we're going to do any sort of test, let's go back to the data set. The first thing what we should note is that our sample size is fairly small. We've got 20 of one, 20 of another. We're, certainly within range of being able to use the central limit theorem, but we really should look at our data first. So let's go over to graphs, and then we'll go to legacy dialogues and the box plots. So where are the box plots? Here we go. and simple box plots will work. We'll put the sample in the category box, we'll put weight up in the variable box, and hit OK. Now, what we see is a couple things. So first off, the medians are not that different. So maybe the median weight after the intervention is just a tiny bit higher, but not by much. Second thing to note is there are no outliers, no horrible skewness, but the other very significant or important thing to notice is that the variances have changed. So before the intervention, we were much more consistent about the amount that we were putting in every bar. After the intervention, there's substantially more variation. So we've done something to destabilize the machine, is the story. So, in summary, it looks like the variance is higher, not much of a difference between the typical values, and we don't need to worry about horrible skewness or outliers, any of those problems in this particular instance. So the way to get everything we need to answer these questions is to go to the independent sample t-test option. So let's go do that. We're going to go up to Analyze, and then Compare Means, and Independent Sample t-test. Now the weight will be our test variable. We're going to copy sample into the grouping variable. One issue is that you'll see you can't hit OK yet. The reason is you have some question marks that have to be filled in. You click on Define Groups. I defined before as the value 1 and after as the value 2. So go ahead, continue after you've done that, and now you'll see that OK is lit up as indicating that we can click on it. So let's go click on it. I like to start by looking at my descriptive statistics. So you'll see that we have a sample of 20 of each, which corresponds with what I saw in the raw data. The mean after the intervention is just a smidgen higher than the mean before. So that's suggesting there's not much of a difference there. When we look at the standard deviations, it also confirms what the box plots told us. The variation is much higher after the intervention than before. And so that was reflected by the fact that this box plot is so much larger than that box plot. Now let's go down below and look at the output. The output, you must pay careful attention to all of the details in the output. So you have really two sets of columns. One is labeled the test for the equality of variances. The other one is labeled the test for the equality of means. You also have two rows. So the two rows are for equal variances assumed and equal variances not assumed. Now, the sig column always gives you the p-values. In this case, the p-values are the same, so it doesn't really matter which one we use. However, let's just think through which row would be the right one to use. So the box plots and the standard deviations have suggested that the variances are different. Therefore, we should not assume equal variances, and our p-value would be 0.734. So let's go take some notes in the Word document, and I would say that the p-value is equal to 0.734, which is greater than 5%, so we cannot reject H0. We have no evidence to say that the means are different before and after the intervention. There we go. An alternative way to do that test, and I guess we're following the book a little bit more closely, is to go look at the confidence interval for the difference. So we see that the confidence interval is minus 0.03 to positive 0.02. And so you could also say, note that 0 is in, was it minus 0.03 to positive 0.02. So we cannot reject a difference of 0. All right, and then the rest of this is exactly the same. There's one other thing that I want to go over with you, and that is this equality of variance box. So the hypothesis that this is testing is as follows. Let's go over to the scratch pad for a second. I guess we could do this in Word as well. But this is testing H naught sigma before squared, that's a B, equal sigma squared after. And the alternative is that they're not equal. All right, and you get that hypothesis from this language that the variances are equal. Notice that the p-value is 0.021. So let's go write that down, take a few notes. So p is 0.021, which is less than 5%, so we reject H naught and conclude unequal variances. So really there are three ways that we can conclude that we should be using this unequal variance row. So the box plots give us a strong hint that the variances are unequal. That's supported by the standard deviations. And these two columns give us a formal test indicating that we should not be assuming equal variances. And therefore, when we test the means, we should be using this, this p-value. All right, so in summary, no change in the mean, but our intervention has made things less stable.